Okay. All right, so you just kind of follow along with me. We're starting on the first page. Oh man, oh here it is. Okay. All right, guys. So we're going to balance the decomposition of sodium azide shown above. It's nice to start here with these nitrogens. So I'm going to put a 3 here. Then I'm going to put a 2 here, and I'm going to put a 2 here. That's nice and balanced. Okay. Determine the mass of sodium azide needed to fill the airbag. Okay. So first off, we're going to do a BCA table for this. So I got 2 NaN3 is going to react to produce 2Na plus 3N2. So I'm going to go B, C, A. I'm going to put my line here. Okay. I'm going to go through here like so. So what I really want to figure out is what is my mass of sodium azide needed to fill the container. So the container was 52 liters. Well, what I'm going to do over here in my mole conversion section is I'm going to use PV equals nRT to find the moles of N2. So N equals PV over RT. So I know that my pressure of the gas was 3.30 atm. People come in here, then we'll just 3.30 atm. Hey John, do you have class in here next?
I've got lunch.
Is that okay if I work in here with this guy?
Yeah.
Is that cool?
Well, you don't want us in here.
No worries. Okay. 3.30. Hey, are you gonna have students come in?
I don't.
You don't think so? Okay.
Somebody was looking for me supposedly, but.
Okay. So we got 3.30. We're just recording a video. Hopefully it's okay with you. 3.30 atm filled to 52.0 liters. So I'm going to multiply that by 52.0 liters. I'm going to divide that by the ideal gas constant, 0.0821. And I'm going to multiply it by my temperature, which is going to be 273 plus 300. So that's going to be 573 Kelvin. When you do that out, that's going to give you the moles of nitrogen gas, which looks like it's 3.65. So 3.65 moles of nitrogen gas. Okay, so we're going to use this then as our reference. We don't really care about the Na in this case, so I'm going to subtract 3.65 here, leaving us with 0 moles there, and I'm going to add 3.65 moles here, but I got to multiply it by that reference in this case. So the relationship is 2 divided by 3. That's going to leave me with a certain number of moles. So 2/3 of 3.65 is how many moles? We got there. 2.43. So I'm left with 2.43 moles of sodium azide, but what I need to do is convert that to grams. So 1 mole of sodium azide is sodium plus 3 N's, 65.02. You got 14 times 3 plus 23, and that's what's the molar mass though?
65.02 grams.
65.02 grams, leaving me with a mass of 158 grams of NaN3. I'm keeping it to 3 significant figures, given the presence of 3 significant figures in the problem alone. So this was a reverse BCA table. The key thing here, this was gas stoichiometry. So what we needed to do was use PV equals nRT first to figure out moles, and then just do it backwards. Okay. In rare cases, it says the sodium azide does not fully decompose, and the bag is inflated to a lower pressure of 2.9. Okay, so this would be our P2 in this case. If all the other variables are held constant, what volume does the defective bag inflate to in liters? So we're looking for V2. So our equation is going to be P1 V1 over N1 T1 equals P2 V2 over N2 T2. Our moles are constant, our T is constant. So our first initial pressure, which was given, was 3.3 atmospheres. And we know the initial volume was 52 liters. Okay. If the pressure actually dropped because the azide did not fully decompose, what is our new volume? So if we think about it, the volume should actually perhaps be a tad bit bigger. So what do we got? No, a tad bit smaller. What do you? No, hold on. What do you got?
45.69 or 7.
How does that work?
So
This times this equals that times that. You should divide 3.3.
wait, it should be. I don't think it should be smaller, right? Because we have a lower pressure. 3.
Times
That would give
52.
59. But that
Yeah. So this would give us 59. I know, it doesn't make sense. The problem was worded poorly. Because we really should be talking about the external pressure in this case. Right? In rare case, it does not fully decompose. The bag is inflated to a lower pressure. So remember, when we're talking about Boyle's law, it's really the external pressure that we're dealing with. So this in this case would be P over V. So that doesn't necessarily relate that well. But for the sake of this problem, in terms of doing the algorithm, we're going to stick with this. So this problem was poorly written, okay? Because the volume should really go up. But in this case, if you follow the algorithm, I'll make sure that it works right on the final. So we're going to stick with that for right now. So according to the reaction, the decomposition of sodium azide is highly exothermic. Explain why this reaction is ideal for the expansion of a contained gas. Cite related postulate to the kinetic molecular theory. So one, we know that N2, if we do the Lewis structure, looks like that. So first off, this is a non-polar gas, so it has weak London dispersion IMFs. We know that N2 has only 2 energy levels, so we know that it's a small gas, so it has very low polarizability. Thus, weak LD IMFs. Okay, and since the reaction is exothermic, we know that the environment is hot. Okay, and that's ideal for a gas. It maximizes the kinetic energy of the N2 particles. So because it's a hot gas, it's going to expand because it's got a low polarizability. The London forces are weak, it's going to expand, and obviously it's nonpolar, so it doesn't have any dipole-dipole forces allowing it to expand. Okay, so whenever we're talking about the kinetic molecular theory, we always want to talk about the environment. Is the temperature high? Is the pressure low? We want to talk about the structure. Is it nonpolar and small? And that elasticity is sort of an assumption we can just assume. We don't have to really mention. In addition to nitrogen gas, the decomposition of sodium azide produces sodium metal. And they want us to draw the photoelectron spectra for that. So what we're going to do is put the relative number of electrons on the y-axis, and we're going to put the ionization energy here. Sometimes you're going to see this referred to as the binding energy, how hard those electrons are held to the nucleus. I'm going to go ahead and call the right side my high side and the left side my low side. The electron configuration for sodium is 1s2, 2s2, 2p6, and 3s1. So my 1s2 peak is close to the nucleus, so it's going to be on the higher side. I'm going to leave a space as we jump to the second energy level, same height. Then we're going to have one that is 3 times as tall, and then we're going to jump to the third shield and have that 3s1 that is lower. On the same axis, using different colors, draw the photoelectron spectra for the magnesium atom. So we know that magnesium is the same thing here but ends with 3s2. But more importantly, we know that while sodium has 11 protons in that third energy level electronic structure, magnesium has 12. So although they're both pulling on that third shield, magnesium's pulling with a stronger nuclear charge. So it's going to have a spectra where each peak represents a greater amount of energy required to pull off those electrons. So I'm going to use a dotted line here for magnesium. There's the 1s2. There's the 2s2. There's the 2p6. And there's the 3s2, a little bit higher. So shift it to the right, given the additional protons in that second energy level. The below chart shows the first three ionization energies for sodium, magnesium, and two other period 3 elements. So which element is sodium and which is magnesium? So we know that sodium likes to form a +1 charge. So what that means is out of sodium's 11 electrons, the first one is going to come, the first ionization energy is going to be pretty easy to remove, all right, that first electron. So it's going to have a lower value. But all the subsequent ionization energies, all the way down to the 11th, are going to be high values. So we're going to see a big jump between the first and the second. That is element 2. So we know that sodium is element 2 in that case. Magnesium, we know in order for it to achieve the configuration of neon, it has to lose 2 electrons. So that first ionization energy is going to be fairly easy to lose it. The second one is going to be fairly easy to lose it. And everything from the 3rd to the 12th is going to be a high value. So that looks like it's going to be, is magnesium not on here?
What about 3?
I don't see it. Is that a big jump though?
Yeah, that's like.
Oh, there's the big jump. Yeah. So the big jump happens here, there. So we know that element 3 is going to be magnesium in that case, because it had a large increase in ionization energy between the second and third, symbolizing that it relatively easily sheds that third energy, those third energy electrons. Okay, so you're looking for that big jump. These kind of charts are used for cations primarily, things with positive charges, because it's really easy to see where that jump might exist. Going on here to G. The decomposition of sodium azide is just one of many processes that harnesses the stability of the nitrogen gas molecule. The Haber process shown below is the most common means of commercially producing ammonia, NH3, from a reaction between nitrogen and hydrogen gas. So let's balance this reaction. We're going to do that by putting a 3 in front of the hydrogen and a 2 here. Sometimes people like to see that 1 there. So we did it. So we're going to do a BCA table here. So if, let's write it right now, 3H2 goes to 2NH3. So before, change, after. So it says if 10 grams of nitrogen is allowed to mix with 10 grams of hydrogen gas at STP, we know that's 1 atmosphere and 273 Kelvin, really 0 degrees Celsius plus 273. What mass of excess, how much ammonia gas, what volume of ammonia gas is produced, and what mass of excess, if any, remains? So this is a pretty simple limiting reactant problem. The first thing we need to do is convert the 10 grams of nitrogen to moles by dividing 10 by 28. And do we have that number? Yeah, that's 0.357 moles. The next thing we need to do is convert the grams of hydrogen to moles by dividing 10 by 2, the molar mass of that, and that is 4.96. And you're getting that because the molar mass of hydrogen is really not just purely 1, it's 1.008. And we have 0 moles of ammonia. Okay. So now what we're going to do is we're going to pick our reference here. You can do it by seeing which one would give you a negative number. I can look at this and see right away that we have way too much hydrogen. We really only need 3 times as much hydrogen, and we have way more than 3 times as much. So I'm going to choose nitrogen as my reference, or my limiting reactant. So here I'm going to go negative 0.357 moles. That's going to leave me with a completely consumed amount of nitrogen gas. I'm going to subtract that from negative 0.357 multiplied by the mole ratio, which is 3 over 1. And what I need to get here is 4.96 minus 0.357 times 3. And let's see if we got that. That's 3.89. Okay, so we have 3.89 moles. Okay, so that's really going to lead us to that second piece, the mass of excess. And over here, I'm going to go plus 0.357 multiplied by 2 over 1. And what amount of moles is that going to give me? 0.719. 0.714 moles. Okay, so that's the essence of the BCA table. Now they say, at STP, what volume of ammonia do I make? So what I'm going to do is I'm going to plug this into V equals nRT over P. So our N is 0.714, our R is 0.821, our T is 273, and our P is 1 atmosphere. And that should lead us to a volume. What is that volume? 0.714 times 0.0821 times 273. 16.00 liters. Okay. Now, because this is a video, I'm going to show you the other option for doing this. Okay. The other option is to take advantage of the relationship that any ideal gas at STP occupies always 22.4 liters. So I could literally take 0.714 moles and say that in every 1 mole there's 22.4 liters. And that's the same thing. If you do that, you multiply 0.714 by 22.4, and you get a number of 15.99. So you get a number very close to 16. To be honest with you, I really am a fan of just using the PV equals nRT equation and unpackaging STP into its values. Again, this is nothing new. It's just a BCA stoichiometric table. Exiting using PV equals nRT, or in the case of the first problem that we did up here, we entered using PV equals nRT. All right. So now it says, using the table of bond energy shown below, determine the enthalpy of this reaction. So this is something people really struggled with, but I don't think you are going to anymore because you've gotten so good at drawing Lewis structures. So here we go. We have N2 plus 3H2 goes to 2NH3. So to get the delta H, what I'm going to do is I'm going to take the sum of all the broken bonds. So in this case, this is N plus 3 hydrogens. And I'm going to subtract that from the sum of all the formed bonds. And in order to do that, what I really need to do is draw the Lewis structures. So I have those. The energy it takes to break that triple bond in nitrogen is a lot, because you have a bond order of 3. Breaking that hydrogen bond is not a lot, because you have a bond order of 1. Okay, so that's going to give us a number. Can you go ahead and give me this number? What is 941 plus 3 times 436? 2249 kilojoules per mole here. And I'm going to subtract that from this. Remember, this is going to be the 2 value times 3 NH's, 390, is that 391? 391. So it's really 6 times 391. Can you go ahead and give me that value? 2346. So if I subtract 2249, which is the energy of the bonds broken, minus 2346, which is the energy you get when you make those bonds, we get an overall enthalpy of negative 97 kilojoules per mole. Okay, so explain the relative strength of the bonds. Well, let's go ahead and draw a potential energy diagram to do that. So if we have energy on the y-axis and reaction coordinate here, we started off at some value with the N2 and the 3H2. And the activation energy, or the energy required to break the bonds there, was 2249 kilojoules per mole of the reaction. And the energy you get when it's formed is 2346. So this is rising and this is falling. So obviously the energy required to break the bonds, or the relative energy of the bonds in the reactants, was less than the energy released, or the relative strength of the bonds in the products. Okay, and it really helps to draw one of these diagrams so that you see the difference there is the enthalpy. Okay. So when you're doing a problem like this, watch out for the Lewis structures when you have a coefficient in front of some multi-atom compound like ammonia. A lot of times people will put 2 times 391 and they'll forget about that 3 inside. Okay, so complete this table below for the Haber process. We've already done that, so the bond order is 3, the molecular geometry is linear, and the IMF's present. There's just London dispersion forces in there because it's a nonpolar molecule. Hydrogen, like this, the bond order is 1. We know that's a linear molecule, and again, just London dispersion, IMF's there. Nitrogen, ammonia looks like this. We know the bond order is 1. This is your trigonal pyramidal shape with that lone pair, or unshared pair of electrons on the top of the nitrogen. The strongest intermolecular forces present here are dipole-dipole. Now again, yes, these have the ability to hydrogen bond, but we don't need to worry about that as much because we're not comparing it to anybody else in this case. So the shortest bond length here is nitrogen, because it has the highest bond order. Lowest boiling point in this case is going to be H2. Next is going to be N2, and this is going to be NH3. Okay. We're starting with London dispersion forces and going down here to dipole-dipole forces. So that's dipole-dipole forces are stronger forces between particles. The reason nitrogen is going to be before hydrogen has to do with size. So nitrogen has a greater polarizability than H2, thus stronger London forces. Okay, so given the fact that the London forces are weaker than ammonia, we get hydrogen and nitrogen having a lower boiling point than ammonia. And then given that nitrogen has a higher polarizability than hydrogen, its London forces are stronger. Okay, and then rank the species in order from least to most ideal. So this is going to be the reverse. That's the least ideal, and that's the most ideal. We know that ideal gases want to expand, so this thing here has the weakest IMFs, and it's the smallest. Really, its size contributes to the decrease in the IMFs there. Does that make sense? You kind of just say that it's hard to say that it's nonpolar and small. It's the smallness of it overall contributes to the weakening of the London forces. So this is why we looked at gases immediately after talking about intermolecular forces, because in order for something to be a gas and to understand what makes it ideal, meaning what allows us to leverage the ideal gas law equation, we really need to understand that the between forces are the things that inhibit or amplify the ability for something to expand. In its liquid form, ammonia is highly soluble in water, so draw and label an interaction diagram for that. So we know that ammonia is polar, so that means that you're going to get partial positives and partial negatives here. The partial charge is due to the sharing of electrons, and the negative means that those electrons are actually closer to the nitrogen than the hydrogen. We know that water looks similar to this, and it's that head of water that's going to line up right there with that hydrogen. Okay, we could also draw it, a hydrogen coming off that nitrogen, and that's a dipole-dipole force, and specifically it's a hydrogen bonded dipole-dipole, because remember, H connected to O, N, or F in a dipole sort of way with dashes yields a hydrogen bond. Okay, so now prior to combining to form ammonia via the Haber process, nitrogen and hydrogen gas must be purified in separate containers as shown below. So indicate whether you agree or disagree with the below statement. Both nitrogen and hydrogen gas have the same velocity. So I'm going to disagree. This is really tempting because they're at the same temperature, and a lot of people think that temperature represents the speed of the particles, but it doesn't. It represents the kinetic energy. So they have the same kinetic energy because they are at the same temp. Okay, but nitrogen has a lower velocity given larger molar mass. So in order for hydrogen to assume the same kinetic energy or the same temperature, you can extrapolate to that, as nitrogen, it must move faster. Conversely, nitrogen doesn't have to move as fast as hydrogen to assume that 298 Kelvin. Calculate the pressure exerted on the walls of each container. So P equals nRT over V. So let's do that first container. N, 0.1, 1 liter, 298. So 0.1 multiplied by 0.0821 multiplied by 298. What was the volume there?
1 liter.
1 liter. Okay. Both of them have the same conditions, so we're going to have the same pressure in both containers, which is going to be 2.45. Okay, so we have 2.45 atmospheres. Okay, determine the new pressure. Okay, if 0.1 grams of nitrogen gas was added to the container on the left, keeping all other variables constant. So what we need to do is convert those 0.10 grams of nitrogen to moles. So 0.10 grams of nitrogen divided by 28 grams per mole equals what? Divided by 28 is 0.0036. So we have 0.0036 moles, okay? And we added that to what was already there, right? So we already had 0.10 moles. So what is that going to be, Kahneman? Well, what's the new moles? I'm sorry.
New moles is 0.10036.
0.1036, right? Or is it 0.100? Oh, yeah. This is, no, because 0.1.
Oh, sorry, yeah, 0.136.
0.1036?
1.
Okay. So now what we're going to do is plug that back in. So we got 0.1036 multiplied by 0.0821 multiplied by 298 divided by 1 liter. So the thing about this is we added that 0.036 to it. A lot of people are going to simply add that 0.1 right in here. Now, serendipitously, the number of moles in this case actually was the number of grams, but that was just luck. So what is this value, Kahneman, for the new pressure?
2.53.
2.53 atmospheres. We see that it went up, and it went up because we added more moles, keeping all variables constant. So that makes sense. Keep the container the same, keep the temperature the same, put more gas inside. There's going to be more collisions with the walls of the container. Next question. When those 0.1 moles of nitrogen in the container on the left are replaced with 0.1 moles of sulfur dioxide, the actual pressure is measured to be slightly less than the calculated pressure. So the key thing is they say, explain using the kinetic molecular theory of gases. Well, we know that nitrogen is nonpolar. It only has LDs, given this question up here. So the key thing when you get something like this is to really attack the polarity of the molecules. That's why that's the first postulate of the kinetic molecular theory. So we know that this is nonpolar. Well, if we draw the Lewis structure for SO2, we end up with this. And as a quick reminder on that, the number of total electrons in this case is 24, minus the number of valence electrons in this case, which is 18. you're going to get 6 electrons available for bonding, locked in covalent bonds. That's going to give us 3 bonds. So we get this molecule here that exhibits resonance. It's got a 1.5 degree bond angle, but the main thing here is it's bent. This molecule is polar. Okay? So what's going on here is all of the neighboring sulfur dioxide molecules exhibit this dipole-dipole force, so they're not going to expand as much. Okay, so the pressure is less due to decreased expansion of SO2 gas particles, given SO2's polarity, and thus its dipole-dipole forces. So when you have an ideal gas, and we saw this a lot with water vapor, it doesn't exhibit or exert that great of a pressure on the environment. Okay. In addition to nitrogen gas, a common source of nitrogen found in food is nitrate and nitrite. So provide the Lewis structure and molecular geometry for both. So the Lewis structure for nitrate looks like this. And the Lewis structure for nitrite looks like this. Okay. This molecule here is trigonal planar. There's 3 things on the outside, no lone pairs. This molecule is bent. Now, this molecule has 3 resonance structures, which I really want you to get in the habit of drawing with equilibrium arrows. Same thing here. Remember, when you're doing the Lewis structures for this, both of these will get 1 additional valence electron. And also, please remember, since they are polyatomic ions, to put them in brackets. Okay. Is the NO bond length longer in the nitrate or the nitrite ion? So with NO3, we have a bond order of 1.3. This bond could either be here, here, or here. With NO2 minus, we have a bond order of 1.5. Okay, so this one here has a higher bond order, therefore it's a shorter bond. So nitrate, it's got a lower bond order, thus less bond overlap and a longer bond. Okay, so that concludes this. When we look at these things, there's a couple things I want you to point out. In terms of the gases, yes, we didn't do that many gas stoichiometry problems in class, but we've done a lot of BCA, and we know with BCA we need things in moles. PV equals nRT has an N in it, so it's a perfectly reasonable way to get moles. Other things for you to really pay attention to are this idea of the ideal gas being something that is often expressed at standard temperature and pressure. So please expand on that to say that that's 1 atmosphere and 0 degrees Celsius, and don't be afraid to use that volume to mole relationship of 22.4 liters per every 1 mole. When doing bond enthalpy problems, watch out for the bonds, the intramolecular bonds within a molecule when multiplying it by the coefficient, seen here with ammonia. And remember that ideal gases are ones that minimize the intermolecular forces and maximize the kinetic energy of the gas particles. Hopefully that was helpful.